So I want to talk to you about the work of many people over the last almost 10 years that relate geometric measure theory and algorithmic information theory. There was a very good talk by Jacob Fiedler yesterday, and I presented his latest results on this connection. And at the end, I didn't have time, but I wanted to ask him, so which journal are you going to send this to? Are you going to send it to a journal on geometrical measure theory, or are you going to send it to a logic computability journal? Let's try. I don't know which his answer would be. You can answer.
GMT.
GMT, okay. But I think this is very typical CIE. So this is a very, I think it's an important job, important work for both areas. So my plan today is to introduce a little bit, everything is going to be probably low level, GMT, a bit of geometrical measure theory, and then talk about the algorithmic information theory part. And then I'll try to go a bit further, so I won't disappoint some of the people that already know this stuff. So I will, but just ask questions or get something interesting out of it. So just to start, at the end of the 19th century, beginning of the 20th century is when mathematicians started to formalize ways to measure the set of subsets. So what it was first called measure theory, so some trying to generalize the idea of the size of geometrical objects. So the thing is that when you have a measure, there is a corresponding family of subsets that are those for which the measure is particularly useful because it has perfect additivity properties, so they are measurable. And this is one of the initial, limitations that only measurable sets are really what the measure captures. And then also, of course, when you have some sort of size estimations, when you have minimal size or maximal size, well, you don't get as much information, in terms of comparing things. If you compare two things and they are both minimal size, they are both small, but which one is smaller? Okay. Then around the same time, so today I'm going to be mostly talking about Euclidean space. Around the same time, a bit later, what happened is that several people started looking at objects in which, measure theory wasn't really the right thing. At least it was limiting the applications you could do. So they started looking at geometrical measure theory, which is built on measure theory. So instead of having a single measure, you have a family of them. They don't have to be measured. They could be something slightly weaker. But instead of trying to use each individual of these measures to estimate size, what you're going to see is at which point in the family of measures you notice a change. Okay, so a change in the size of the set. So there's usually a parameter, that's parameter S. So for different values of S, your measure is going to be like a bit more accurate, at which point it starts being too big or too small. So this is kind of what you're looking for. And this is what was captured by the idea of dimension. So let me show you the original definition by Hausdorff in 1919 that you may have seen before. So don't worry about the details, but let's see if I can. Okay, so this quantity here, HSE, is defined for each subset of the Euclidean space, and it's called the S-Hausdorff measure. And it kind of explains a way of covering the set E, that has S as a parameter. In this case, well, you can see that the parameter S is here. So somehow the size that is corresponding to E is taken to the power of S. So as you can imagine, if S is, we are talking about very small diameters. So if S gets towards 0, you're going to have a huge quantity. If it goes towards 1, it's going to be a bit more reasonable. And what you want to know is which is the point. So the value S, the infimum of all S for which it is 0. So it's clear that it's going to be infinity first, and then at some points it goes to 0. Okay, there is another similar quantity in geometrical measure theory, sort of dual, that I will not be talking too much today, but just for completeness, it's called packing dimension. It is also related to a family of outer measure, in this case, the packing measures. And it's always bigger than partial dimension. We'll maybe say more later. So, okay, so what happened with these concepts is that they became very popular when studying sizes of objects such as these nice drawings here. They are called self-similar sets. And these are the very 3D examples that all the mathematics book have for sets that have values of dimension that are non-integer. Okay. But there are far many more different areas of mathematics, even of physics, for which estimating the dimension of a set is a very important problem. It's usually connected with size. So somehow remember that you can define the dimension of any set. So there are no limits. You don't need the set to be measurable in any way. Every set has a dimension. And this is very useful in several contexts. So my plan today was just to give you a couple of a couple of examples of geometrical measure theory properties or conjectures, and then start talking about what is the algorithmic information theory side going to say about those. So this is the first one. So the dimension of Cartesian product projections is not, it doesn't have a very straightforward behavior, because of the covering nature of the definitions. So for instance, this property that was first proven by Marström for R2, and then by Mattila for the general case, is not at all obvious. So let's read it. So you have a set. Okay, well, it says that it needs to be analytic, but we'll get into that later. And it has a value of dimension S. So half of dimension of this set is S. So I'm going to look at the projections of this set into all the possible directions. So if the set is in Rn, I will project to the points in the N-1 sphere. Okay, so in each of the directions. So for most of them, the dimension is going to be as expected. The dimension of the projection of the set E to the direction literally is going to be the minimum among S and 1. Of course, if you're projecting n dimensions to n-1, you're going to get at most dimension 1. Okay? So the interesting case is when S is less than 1. Okay? So for most of the directions, you're going to get the projection has dimension S, the same dimension as the set itself. So this property does not hold for arbitrary E, assuming the continuum hypothesis. And recently, well, maybe not so recently, time is going fast. A few years ago, Stuhl and Lutz proved an extension of this. Okay? So this extension is one of the first examples of how we can use algorithmic information theory to prove results in geometrical measure theory. So my plan is to tell you a little bit quickly, not very long, about how this proof is done. The second case I'm going to be looking at is the famous Kakilla conjecture, which has a simple statement. Of course, if you have heard about it, it's not simple statement doesn't mean a simple solution. And this is completely open for the case n bigger than 2. But let's not get ahead of myself. So you define a Basikovich set. It's a set in the Euclidean space that has for every direction you can take, so that is every direction is in R n-1. It contains the unit segment. So it contains a piece of size 1. Okay, so this set, Basikovich already proved that there exist examples of Basikovich sets that have measure 0. So it can be very small in the sense of measures. So the question is then, what can dimensions say about them? Okay, and the conjecture is that if you consider dimension, such a set says that for every direction you have a unit segment, has to be maximal dimension. So this is called Kakilla conjecture. This has only been proven for the cases n equal to 1 and 2, and it's open for n bigger than 2. There are several lower bounds. There are several lower bounds, and it's a very interesting problem that has created a whole, I would say, area around it. That of course is GMT, but also very connected to harmonic analysis. Jacob could tell you more about it, but my plan today is to tell you how the case that's already known, how it is proven for with algorithmic information theory methods, and if you can see the difficulties in extending this. So this is like my second. So let me start by giving you very quickly just the main definitions, in case you're completely new to this. Just tell you Kolmogorov complexity is defined for finite strings, and it consists on the amount of information the string contains. What does it mean, the amount of information? Well, there is a fixed Turing machine, and you're looking at the size of the smallest input that gives you back your string. So kind of the essential information content within the string. This is a very useful concept in many areas. Personally, I come from computational complexity. So for us, it was extremely useful when building examples of that had maximal information that were extremely useful for combinatorial purposes. It was the idea is that, as I tell you here, the Kolmogorov complexity of a string sigma is at most the length plus some fixed constant, and most of the strings are incompressible, meaning that the Kolmogorov complexity is at least the size of the string minus some number of factors. And it's pretty useful in many proofs to say, let's take an incompressible string within this set. And the reason why this incompressible string exists is often, at least partially, deduced through counting. Okay, because most strings are incompressible. So if you have enough, you're going to find an incompressible one. There are many interesting properties that help you deal with this quantity of information in a natural way, including things like that allow combination of several strings, symmetry of information that kind of compares the amount of information one string has about another, and vice versa, etc. For the purpose of today's treatment of the Euclidean space, well, I forgot. You can relativize things. So you probably use two oracles. The Turing machine can have an oracle, and the full concept is robust to this. So you have Kolmogorov complexity of a string relative to the oracle. This is going to be very useful later. But this is for strings, and for Euclidean space, it is far more useful, at least easy to deal with real numbers through approximations, as opposed to just looking at, finite prefixes of real numbers in the sense of a real number as a sequence of digits. Okay, it's better to look at this quantity here, which is also Kolmogorov complexity. We read it as Kolmogorov complexity of the real number. Let's say it's a real number x with precision r. It means that you're looking at the rational points that are very close to x, and for those, you choose the one that is easiest to describe, that has the lowest Kolmogorov complexity. Okay, so it is the smallest Kolmogorov complexity of a point, of a rational point that is at distance 2 to the minus r of x. Rational points are like sequences, right? They are like finite sequences in many ways. Okay, so you can look at the finite coding of the rational number, and this is what you want. You can also have oracles here, no problem. So once you have this, okay, so you have Kolmogorov complexity of a real number at precision r. Now you can have what is called effective dimension. If it's called effective dimension, it means it is an effectivization of what I described you from GMT. Also, I'm going to use Martin law of randomness, which is an important concept of its own. But for today, let me just say that it can be defined or characterized just by looking at the Kolmogorov complexity at precision r. For all r's has to be maximal. Okay, this is maximal krx. So effective dimension can be now defined as the information ratio. Okay, so here you have for a point x, so for real points, you define the dimension of the points. So this is a bit different from what I describe as coverings for sets. So this is I'm doing it point-wise. This is an important difference of this effectivization from the classical concept. Okay, so I'm just looking at the dimension of the point x as the best case compression ratio. So, yeah, best case in the sense that the more you compress, the better. It depends on which side are you in. So for points, you define it through Kolmogorov complexity, and then you do the for sets, you just take the supreme. Okay. So this can also be done, of course, with an oracle. That's okay. So we have this effectivization. As I tell you, well, also since I have introduced Martin law of random, Martin law of random have effective dimension 1. That's very clear because they have maximal Kolmogorov complexity at all r. So that's going to be 1. Actually, they could have. And also, you can also effectivize. I mentioned packing dimensions, kind of a dual. Okay, there's an effectivization, and the only difference is that instead of taking the best case in the compression sense, you can take the worst case. Okay, that's good. Very simple. So, why did we do this effectivization of dimension? First, it is an effectivization. It is very clear that it gives you an upper bound on the half of dimension. I mean, I haven't proved it or anything, but it is kind of natural to think that what we're doing in a twisted way maybe is the covers in the definition of half of measure, etc., to some sort of computability restriction. Okay, so at least whenever you use effective dimension, you have an upper bound on the dimension of the set. Oh, that can be useful. Then, of course, what happened is that when we started with effective dimension, is we were very interested in, especially in subsets of the computable points. So we were thinking about complexity classes. We have heard about those, and we were trying to estimate sizes of one class within the other. So everything was, of course, half dimension 0 because they were countable classes. We wanted a setting in which we could have a meaningful size definition. Yeah. So this was kind of the second thing we did, is get results on the dimension of this class within this other, which was useful in many ways. For instance, if you had one class within the other of different dimensions, it was very easy to construct elements that were in one class and not in the others. So that was the first purpose. Then there were many sets for which somehow the way we could estimate this effective dimension would give us a point-wise analysis. You know, it was like saying which are the most difficult points in this set. Okay, and this sounded, it was giving us a lot of information on the structure of the set itself. Then what happens is that also in many cases, effective dimension and half dimension coincide. In which cases? I mean, many. Well, it's not a good word, but in the cases of simple sets. So, for instance, the nice drawings I was showing you, the Sierpinski triangle or the Goff curve, they all have the same effective dimension and half the dimension. Okay, because they have the simple descriptions. So for a while, this was good enough. So it meant that we had a tool. It was useful in computational complexity, and for many interesting cases, it gave us back the original half dimension. But all this changed a lot in 2018 when Neil and Jacques Lutz proved a direct trip back to geometrical measure theory. Okay, so this is a celebrated point to set principles. And what I essentially telling is you can deal with half a dimension using only effective dimension if you're willing to pay for the effectivization. Okay, so let's have a quick look. So you have a set. The half dimension is exactly equal to the best case, so the minimal B, oracle B, looking at the effective dimension of E relative to oracle B. So there is a single oracle that is going to give you back half dimension. It's not clear how to find this oracle, etc., but the existence can be interesting enough because there are many techniques in information theory that relativize very well. If you're willing to pay for the uncertainty of not knowing exactly how you relativize, the combinatorial part of dealing with how compressible things are, that's completely transparent to the relativization. Same happens for packing dimension. So, okay. So what I plan to do is to give you the two examples of GMP. At least have a look at how we would deal with them using effective dimension. That's my first goal for today. So we were looking at the projection theorem, okay, and this is the improvement by Neil Lutz and those two. They use effectivization. They use the point to set principle, okay, and the improvement was instead of having the result for analytic sets, they have it for sets that have the same Hausdorff and packing dimension. In fact, in fractal geometry, they are often called regular sets. Okay, so packing and Hausdorff are the same. If these were effective dimension, it would mean that the worst and best case for the compression ratio were the same. Okay, so we have a set like this. And we want to prove that for almost every E, the dimension of the projection to direction little e is the dimension of the set. So let's stop for a minute and just do this in a couple of minutes. Not the full proof, but like kind of see how algorithmic randomness is with this. So first, let's just think about the case s less than 1. So you have a small set, a set of dimension s less than 1, and you want to prove that if you project it into almost every direction, you're going to get dimension s. Okay? So what do you need to do? Well, you need to show that the dimension of the projection is at least s. Of course, the dimension of the projection is going to be almost 5, so that's not a problem. So let's prove the lower bound. This is an interesting part. So, well, before showing you, let's just think a minute. So one of the main, well, at least at first, what strikes me as the main advantage of effective dimension is that every analysis is done pointwise. Okay, so in order to prove that the full dimension of the projection is at least s, I will have to deal with points. Okay, if I could deal with a single oracle, I will have to find a point for which the effective dimension is at least s. I need to think a bit more about how to do with the oracles, because what the point to set principle is telling me is there is an oracle for which the effective dimension is 1. So, well, I need to think a little bit about the oracle itself. But with the oracle fix, what I want to find is sets, points here that have a lot of information. Okay, so that have dimension at least s. Now this dimension is this information ratio. So how do I do it? Well, the first thing is to choose quite a few of these E. And since we're going to be dealing with information content, we're going to be using this effectivization. Let's start with maximal information points, maximal information directions. That is Martin law. Okay, so, well, first, using the point to set principle, let's try to get a single oracle. Okay, so I can get one oracle for which the house of dimension is the effective dimension, and I can also get another oracle for which the packing dimension is the effective packing dimension. But if you think a bit about it, so the more oracles you have, like if you put together several oracles, you do better. You cannot do worse. Okay, so whenever you have like several oracles that give you dimensions of different parts of what you're interested in, you can just put them all together and get a dimension smaller than all of them. Okay, or at least the minimum of all of them. So we can take a single oracle that gives us effective dimension and effective packing dimension for E. In this could work for any E. Okay, I'm not even using the fact that this E has the same packing and effective dimension. Any E, I could just use a single oracle. Then, once I have this oracle, I'm going to choose the directions to which I'm going to do the projection. I want a measure 1 set of them, because this is what the theorem is requiring. I want many directions for which I can control the dimension of the projection, for which I can show that the dimension of the projection is big. So I'm going to take Martin-Love randoms because they have a lot of information in, and because there is a measure 1 of them. Okay, and I want them Martin-Love random relative to the same oracle. So I can use the oracle in the information theory arguments. So once I have that, what do I need? I need to find a point within the projection that has a lot of information in it. I want to choose like one point in E so that the projection of this point in the direction of E has dimension high, as high as it can be. So how do you do it? Well, first, since fix a single direction E, and again, play the point to set principle again, find an oracle for this particular direction. This is the oracle that gives you back house of dimension. Okay? Now, if I need, I can put together this oracle for the projection of E, together with the oracles for E. Everything can be together in a single oracle. So what do I want? I want a point for which this dimension is as big as it can be. Okay? So I'm going to choose a point in, sorry, okay. Well, the number 4 is what I told you, put together all the oracles. I want to choose a point in E that has as effective dimension as big as I can get. Okay? Since the dimension of the set is the supremo, probably cannot get exactly S, but I could get as close to S as I want. Okay, so I have a point within E that has very high dimension. Now, the information theory part is to try to prove that since I am taking E, that is Martin-Love random, and set E, set epsilon that has this maximal dimension within E, projecting set epsilon to the direction E is going to give you high dimension. It's not terribly hard, but it does require to do the information theory argument, trying to see how much this projection can help you to get both E and Z. So in order to show that it has to have almost maximal information. Okay, so I mean, number 6, of course, is the technical details I'm not giving you, but I think this is very illustrative of how the point to set principle works. Everything is done point-wise, sorry, and the main steps are like choosing the points that will get you the dimension you need. Okay. In this case, the interesting part was choosing a Martin-Love direction, Martin-Love relative to the oracle that suits me. Once I have that, choosing a point that has maximal effective dimension within E with the oracles that were useful for the projection and for the set itself. Okay, so this is like the 2 interesting points is the choice of points. Okay, as I tell you, I cheated. I didn't give you the proof. This is number 6, but I hope this gives you an idea. Any comments? Have you seen this too many times? Okay. Yes, I have seen this too many times. Okay. Okay, let me show you a little bit about the Cajilla conjecture. Okay, second thing. So, as I tell you, the idea is that a Dasikovic set contains a unit interval in each direction. Okay, I am looking at the case n equal to, sorry, yeah.
In the previous argument, where is regularity being used?
It is being used here. Okay, how is it being used? Because the thing is that since somehow the best and worst case of set E epsilon are very close, and that helps a lot to do the projection. So it's kind of you controlling really the approximation to set in all cases. There are better results for the master projection theory, but I just wanted to use this as a good example. Okay, so as I tell you, the Cajilla conjecture, okay? Sorry, okay, here. So you have a set, it contains an interval in every direction. You need a drawing. I'm terrible at drawings. You don't know much about what the set is like, but in any direction you choose, you're going to find a piece that contains an interval in that direction. Okay, and it's only known for are equal to, it was given by Davis in 1971. I'm going to show you what an information theory would look like. Okay. So let's take, well, again, I'm going to, okay, I'm going to try, in order to prove that the set has dimension 2, I want to find somehow points in the set that have high effective dimensions. That's the idea. How I'm going to do that? Well, since the set contains an interval in every direction, I'm going to try to get like as much randomness as I can in a point in the set. So in order to do that, first I'm going to choose a direction. I'm going to choose a direction that has a lot of information in the direction itself, okay? Since the set E contains an interval in every direction, it's going to contain an interval in the direction of E. I'm not I will just stop. Okay, so there is a 0, 1 interval in the direction of E that is contained in the set. So for instance, I don't know if this is this needs a drawing. Yes, very quick one. So the thing is that we are in R2, E is just a direction. So somewhere in the set, there is an interval, there is a 0, 1 interval in the direction. Okay. So the thing is that an interval is a lot. Okay, within an interval, you have many random points, many high dimension points. You know, because the interval, I mean, if you look at the interval 0, 1, just in the real line, there are many interesting points within this interval. So now I just need to choose within this 0, 1 interval of a size, a piece that has a lot of information in it. And since I can also use that I am interested in direction E, I'm going to make this point very random also relative to the direction of E. Okay, so for each oracle B, okay, I fix an oracle, and I'm going to take something that is random relative to oracle B, the direction I have chosen, this direction that I studied being just Martin of random, and the starting point. Okay, it could be, you know, that this starting point maybe had some interesting information in it. Okay, so I want my point to be random also relative to this A. Okay, so once I have that, this is the interesting part of the proof, of course, that I'm going to show that the dimension of the point that is in this interval, that is, you know, choosing a very random stopping point there, has dimension at least 2. Okay. So where is the difficulty of this? What is the difficult part? Or on the in other words, I'm talking so that you can think maybe I'm answering. Why is this okay for n equal 2 and it is not for higher n's? Well, you know, because somehow I'm trying to see which is so this is the point here, the point I have chosen in the direction of E. And this point happens to have high dimension because of the way R2 works, okay? So imagine that this point could be described easily in a different way. For instance, like a different line. If this P was also within a different line like this, like it's very close to the line of direction E, if it's very close, the direction is going to be also quite random because it's very close to E. Okay, but of course, you could have a completely different line for which also P was a point. Okay, you could have something like this. Maybe this other line that contains point P is much easier to describe. But this is the plane. Okay, there isn't that many things you can do in the plane. If this line has an easy description, it would give you an easy description of the direction E, and also even of the rest of the parameters. But this is because you are in R2. Somehow in R2, choices of how lines meet are very limited. This is what helps us relate the information content of different lines meeting the same point. You can try to do the mental exercise of doing this in R3, and it doesn't work. You know, the variety of lines that can be very close within R3 is far more. It's not very clear how to relate the information content of close lines at higher dimensions. And it would be, I mean, really interesting to get further into that. I mean, it's a very interesting question, even if it doesn't have simple answers like we have in R2 still. I mean, it's really, it would be a good advance. But so this, I just wanted to show you like how, so in general, the difficulty of applying the point-to-set principle, I mean, so this is the kind of thing when we started looking at this point-to-set principle, it was just kind of magic, you know, like, oh, I don't know exactly how this works, but it seems easy because you just deal with points. But then you start to understand the proofs that other people have done and the proofs that you could do. And you start saying, okay, so the difficult part is always like in the choice of points within the sets. This is, so in this case of the Kakilla conjecture, how do you get a maximal dimension point within the set? Even if you're very good at picking the random directions, etc., still, there's a way to go there. So I think reflecting a bit about this can be interesting. There are many, many results. 10 minutes, thank you. There are many, many results that have already been proven using the point-to-set principle. I had a list, Jacob added a few interesting ones, especially one I was completely unaware of. I'm not gonna read them all, but let's see, this is like the first, the older ones. You can see by the dates, they are not that old. And in principle, several of them, they have to do with the first ones. They are pretty geometrical. They are looking at intersection, you know, the operation of intersection that is not trivial with relative to dimension, to half of dimension. The Furstenberg sets that are also kind of a bit in the line of the Kakilla conjecture. But then they're also interesting results in other spaces, results on the Hamel basis, finding Hamel basis of any dimension. I think spaces out of Euclidean, and there's a long growing list that I need to learn better about what are called distance sets. Okay, so that the sets of values of the distance of pairs of sets. There are very interesting open problems there, and there's been very recent advances that I think are very good. I will not cover them today, but I advise you to look at this. For instance, you can start with the last papers by Jacob and Don, and go from there. Okay, so I give you a bit taste of what BST looks like, how it can be used, what are the difficulties. I hope at least it was some food for thought. Let me go back to it in a more computability way. Let's have a look at it and see what can we wanna find out from this theorem. So there is an oracle involved here. And with this oracle, house of an effective dimension coincide. I want to know more about this oracle, of course, and there are like the obvious questions, but they are still interesting, I think. How difficult, how easy can this oracle be? Oh, the first temptation is difficult in terms of complexity. But I think that's very interesting. But I'm thinking in a more general way. Like, how hard can this be? Also, next, I will also tell you a little bit about the effectivization itself. But what do I mean with difficult? I really like this concept of optimal oracle by Don Stult in his paper on projection, improving what I told you about the projection theorem. So, sorry. Oh, I didn't want. Apologies. This is what I wanted to stop. Okay, so house of optimal oracle for a set E is just an oracle that gives you the dimension of E. Okay, so house of oracle means that effective dimension relative to this oracle gives you back house of dimension, and also optimality. Optimality in the sense that if you add more to this oracle, you don't get more. Okay. So meaning that if you take another oracle and you put it together with the optimal oracle, there is a point X for which you don't get anything else. And so the cosmogonic complexity of X is at least with oracles A and B is not lower than with A alone. Okay. So let's see, the more oracles you have, in principle, the shorter your description could be, okay? Your Turing machine, your universal Turing machine could cleverly use both oracles A and B and have a shorter description of this particular point X. That is not the case. This is why I call this, this is why Don calls this oracle optimal, okay? So no matter which oracle you add, you don't get more. You don't get more. There is a point for which I think I missed part of the definition. I think the point needs to be, the dimension of the point is very close to the dimension of the, I'm sorry, I think I missed a formula there. But mostly you don't get a shorter description than with the oracle itself, than with A itself. So what happens with these sets that have optimal oracles is that they seem to have very good properties. For instance, in the projection theorem, the one I show you, all the known cases, at least all the cases I knew, there's one I need to check, they all have optimal oracles. So the analytic sets of Marstrand and Matila, the regular sets of Stool and Lutz, they all have optimal oracles. So I think we really should have a look at this kind of sets with optimal oracles and find more about them. There are many GMT properties that hold for analytic sets. Can we make most of them extend with some sort of sets like this with optimal oracles? I think something like that is going to turn out to be true. I think that's very interesting. The last thing, how many minutes do I have? 3, okay, 3 minutes is. The last thing is the computational model is very flexible. Okay, so we already we have proven that you can deal with polynomial time effective dimension or polynomial space effective dimension, if that kind of explains itself, and you still get back house of dimension. But even more surprising, you can deal with finite state dimension, and again get back a house of dimension. This is, for me, very suggestive. I will show you a little bit in the 3 minutes. But remember, I mentioned briefly that geometrical measure theory meets harmonic analysis in a very strong way. There are several, I think, conjectures that imply Kakillas is the right direction, and they are related to harmonic analysis, okay, to Fourier coefficients of different functions related to the set. On the other hand, for us, within effective dimension, I think finite state dimension is the one that seems to have closer ties with harmonic analysis. I think we should really go around this slowly, because even if this is like the weakest computation model, weakest in the sense that less things can be computed, you can just use finite automata and still get back half the dimension. So, well, the definitions are not pretty natural, I would say. So if you have an automata, you can still define information content, like how small is the description relative to this automata. And you can define taking an extra quantifier over the automatas. Of course, the automatas have to be outside of the infinite limit. But to still get something very meaningful is called finite state dimension. And since you're looking at real numbers, I'm not going to get too much into it, but the representation of the real number turns out to be very important, because different bases could give you different values. For instance, because the Borel normal numbers are those that have finite state dimension 1. Okay, so it's like it's weak model in this sense. So the question would be, how do you relativize an automata? But you don't really need to relativize the automata. If you look at the definition of information content, you can see that somehow there's also the importance of this, of how you approach the real number. Okay, so in principle, what you usually do is you look at finite representations of a rational number near X. Okay, but this is what you can change in order to be able to use automata. So you can do just something like this. You can have, as opposed to saying each finite string gives me a rational number. Okay, each finite string still gives me a rational number, but let me parameterize that. Let me say that this correspondence between finite strings and, let's say, rational numbers, dyadic numbers, if you prefer, is something that I can change. It's going to be sort of the relativization. So the oracle is going to be how we represent dyadic numbers. Using that, you get back a point to set principle, etc. So you get back, so you fix a way of representing dyadic numbers. Once you have fixed this way, you have a finite state dimension. And then the point to set principle is take the best representation for yourself. Okay, so your oracle is going to tell you only what this means, what this string means. So I'm going to stop here just by showing you that reminding you very quick computational models, but still can reach half the dimensions. This is the playing with the relativization. And in fact, you can go back and say, okay, so what happens is that you don't use the oracle that much in the effectivization of effective dimension. So it's kind of sort of a single functional way what you're doing. You don't need to do very complicated access to the oracle. So I think that can be useful. And somehow you should really separate, in this cosmograph complexity characterization, what parts you do compression, what parts you access here. Okay, and of course, please solve the Caquilla conjecture. For instance, for R3, I'm not giving you the full list of results that you can easily find. But for instance, for R3, the best known bound is that it's at least 5/2. And you want to go to 3, okay? And this was done by Katz, Lava, and Tao in 2000. So it's been there a while. I think maybe the earliest is slightly younger. The latest bound for bound is 2000 and something. Yeah. Thank you. Sorry, I hope you don't hate me because you probably know much more than I was saying. Okay. So yeah, so the main questions could be, I want to find out more about the oracles in the point to set principle, or if you prefer of this way of enumerating rational numbers. I want to look at these optimal oracles and try to see if they can replace analytic in the GMT proofs. And I want to prove the Kakija conjecture. I mean, it doesn't have to be myself, but it would be, excellent if we could use dynamic information theory to prove the Kakija conjecture. Thank you. Sorry.
Thank you very much. Well, we have about a minute for one question. I understand that we have to, so you have to use this microphone and that one goes to the person who asks the question.
Thank you. So, okay, and you can ask me later also during the coffee break.
Would someone like to ask? If not, we just heard, there is a question.
I don't know.
Okay. That's what they said about these products.
So for sets that do not have an optimal oracle,
Okay.
guess my question is, what one is, do you know that these work as counterexamples, for example, for the projection theory?
Yes,
And-
yeah.
And then the other part of the question is, can you just get such sets easily, or do you need to assume CH or something to actually build that without optimal oracle?
You do need to assume one of these hard axioms. And yeah, Don in his paper, he builds a counterexample through a set that does not have an optimal oracle. Of course, it's not an equivalence, but kind of has a feeling that there's something more, yeah.